Hello, and welcome to this talk with a quite provocative title, Retire Your Tables, It's All JSON now. And as you may see here, I already questioned this title a bit. So is it really that time to retire your tables when you look at JSON, or are there still some reasons why you may want to preserve the relational model in your application? Well, this talk is about data models. I will speak about JSON, why it's so popular, especially in application development these days, but also what you're giving up if you do everything in JSON and why it may be a good idea to also use some relational tables or the relational model where it makes sense. And a little spoiler alert, I will show in a little demo that actually you want to do both. Good. So to illustrate why JSON is really so popular, I thought I'd present you like a sample application. So let's say we want to start an online shop where we start selling used products. Like, let's say we start with books and movies. And there are some common properties for these items, like what is the title, what's the condition, how many do I have, and what's the price. And then there are some properties which apply just for one of these types. So for example, a book has an author and it's written in a language, whereas a movie, you may be able to change the language, and there are some actors, and there's also a format, like is it a DVD or a Blu-ray? And let's say in the future, if our online shop takes off and is successful, we may want to sell some other items like posters, for example, and we don't really know which properties these items would have. So now, from an application development point of view, this is relatively easy. Let's say we start with some Java classes here. There is an abstract class product, which has all these shared attributes. And then with inheritance, I create subclasses for product, for book or movie. And maybe in the future, I could just easily create a subclass for poster, for example. But the moment I would map this to the relational model, I would have to do something that's called a normalization, where I take my business objects and I map them to tables. And these tables are connected with relationships. And for example, you see here that there is a table called movie actor, which connects the movies and the actors. And the reason is that most movies have more than one actor, and most actors also play in multiple movies. So this is what we call an M-to-N relationship. And you can see here this very simple example already yielded us 7 tables. And you can imagine if this application would grow in complexity, we easily hit a few dozen of these tables. So now before you can insert any data, you have to create these tables. So you have to specify the table names, the columns, what are their data types. And you may also want to add some constraints that you say, well, I don't want to erase an actor if there is still a movie played by this actor, for example. So once you've created all these structures, you could insert the data. And now we want to see on the right side how you would do that in the JSON land. So in JSON, you don't have a schema. Instead, the data is self-describing. So all you do is you would create something like a collection. This is basically a bag of JSON objects. And if you insert your data on the JSON side, it's basically this self-contained document consisting of key value pairs. Whereas if we look at the SQL side, you actually have to insert. So the example is we're adding a new movie. So now this movie, the information is shredded into multiple tables, the products table, the movie table, the actor tables, and it's even a bit more complex than that. Imagine you are inserting a movie where an actor already exists in the database. So you need to check this, whether a new movie also adds new actors or if it just refers to existing actors. So it's basically you need to run a query during insert to identify which case it is. Whereas in JSON, you would just inline all the data in one big document. So for example, here we see that the actor is an array of all the actors that are playing in this movie. And if you add another movie with the same actors, it would just get inlined again. And this is what's the key difference here between these data models, that on one hand, I call it inline, the correct term would be embedding, so all the information is embedded in one big document, whereas in this relational paradigm, you basically have links across these entities. So you have a link from movie to actor, and this allows you actually to store the data only once, whereas we're going to see in a second, you would actually store duplicate data if you do this JSON route. But we get to that in a second. So now we've inserted some data. Let's say we want to retrieve a business object. Here the example is we want to find all the movies where Jonah Hill is playing in. So what we would need to do is to issue a query on different tables. In this case, it's product, movies, actors, and this movie actor mapping table. All of these tables would be joined using the right join condition. And then we pick out all these columns that are needed to populate the actor business, the movie business object in our programming language. On the JSON side, this is much easier. All we do is we issue a query by example. So this query is basically a piece of JSON itself. And this JSON is matched against the data inside our collection. So we're looking for all the documents which have a field actor and whose value is Jonah Hill. And we immediately pull out the entire document. There is no reassembly needed in this case. So this example has shown that you don't need to do normalization. You don't need to do shredding at insert and reassembly at query time. And there is another reason for JSON, and this is its schema flexibility. So most of the applications are not perfect initially. There are changes, we've forgotten cases, and this is an example here would be that we say, well, a movie, we would want to store an additional attribute, for example, the year when it got released. And we also made a mistake on our books here. We assumed that a book only has one author, but then we realized that there are books with multiple authors. So we do have a cardinality change here. Author is no longer just a string. It's actually a list of strings. So what are the implications now on our two data models? So in this relational world here, we have a schema change. The year is an additional column in our movies table. That's a relatively benign change, alter table, add column. We may have to modify some queries and inserts, but it's still okay. But if we look at this cardinality change, now we're saying a book can have multiple author. It used to be that the author was just a column in our books table, but now similarly to movies and actors, we have this mapping table, which I call books author. Like one book can have multiple authors and one author can write multiple books. So this is now a more invasive change where not only do I add two additional tables, I also have to modify my queries, my inserts, my updates, and I also have to migrate my old data where I used to have authors being inlined and now they are in a separate table. So this is a relatively big change here. Now, if we look at the right side where we store our data in JSON, it's actually very easy. JSON is schemaless. I can just add a new field, released in this case, and I can immediately query it. So there is no schema that is underlying this collection. It is just that if a document has a new field, I just add it to my new data. Old data doesn't have to be changed, and my queries can immediately use this. This is the example for this additional field. The other example is the cardinality change. And here again, it is super easy. So author, which used to be one string value, is now a JSON array of string values. And again, I don't have to touch my old documents. So some documents may still have author being one string, and my new documents have an array of strings. And the nice part of it is that my query by example expression here, where I'm looking for an author, that works in both cases. So whether my search string is a scalar or if it's an array, it's actually matched against every value inside the array. And if there's one hit, it will select this entire document. So now at this point, you may say, well, JSON is really great. It is schema flexible, so I can do a lot more agile application development. I'm saving all the efforts of normalization and mapping of business objects. So let's forget about tables and only do JSON from now on. But Not so easy. There are still quite a few, actually many use cases where you would want to have a more relational access to your data. And this is very obvious example is if you want to do some reporting of your data or some analytical queries where you are not interested in retrieving an entire document, but you want to extract some information from these documents or to aggregate some new information based on data that's inside. So sounds complex. What is a simple example? Simple example would be give me all the movies for a given actor. And in that relational world, this is actually quite easy. All you need to do is issue a query on these three tables, movies, actors, and movie actor. You don't have to look at any of the other data. You don't have to look at products, etc. And you can just do this with a simple join. Whereas in this JSON world, well, how would you do it? You would probably have to visit every document. You could obviously put an index on it, but normally you would go to every document and then you would have to scan through this array, see if it has this actor. It also, you have to check that the type is a movie. And then you could return, for example, an ID or the movie title. So this is certainly more complex and may also be slower if you don't have like secondary structures like an index. Another example is that this business of embedding data causes data repetition. So in our example, we said, well, our movies, they have an array of actors and we just had the names of these actors in this array. But what if you wanted to store more data inside here? For example, when an actor was born. So now you would have to repeat this for every data set here, like for every actor here. And it's not only that you have to repeat it, that you kind of waste a bit of space, but it is also that inconsistencies would be possible. So what if you change one data set and the other one is still pointing at the old data? Then you have inconsistent data, and you don't also have like a central place where you do these updates. So let's say you wanted to update an actor, you would have to update all the documents that point to this actor. And especially if you use like a NoSQL database for JSON, which is weaker on transactions, etc., this might be quite problematic to have data repetition. Another disadvantage of this embedding is that sooner or later you will run out of, it won't make much sense anymore. So we had a simple example here with a product, a movie with actors. But stepping back, we wanted to build like an online shop where you have orders, and orders are have customer information, and then they order multiple products. So you basically have different entities, purchase order, customer, product, etc. And it wouldn't make much sense to actually embed all this information inside. I mean, you would have massive documents and let's say you would want to update a customer, basically every customer information would be in every order. So this is just a nightmare. So even with JSON, sooner or later, you would want to have store different entities separately, maybe as separate JSON documents, but then you would want to link one document to the other. So for example, here we have a purchase order and it has a customer ID, which points to another document sitting in another collection. But now you are almost doing something that a foreign key primary key does in a relational database. At the end, you would need joins on this. You would want to have referential integrity. So now again, this is the point where relational databases would shine and where a NoSQL database would be quite limited. So what now? So now we've seen JSON is great for application development, but it is quite limited if it comes to analytical queries, reporting, etc. So there is still a lot of strength that the relational model has. So is it an either or question, or can we somehow combine this? And I want to show you now in a demo how you can combine the strength of both these data models. And with this, we are going to use some SQL here, and I am connecting to an autonomous cloud database here. So it's a 21C, always free tier, and you could get the same. And what I'm showing is not this example with products and items and movies. Instead, I have something maybe even simpler, which is a school. So we have a teachers and students and courses, and there are end-to-end relationship between all of these. Like a teacher could teach multiple courses, and a course is typically attended by multiple students, and a student also has multiple courses. So you really have a network model here, which is something that the relational database handles very well. So we start out with something that is quite familiar for all of you, which is a plain relational table. So I called it teachers, and you see there is no JSON inside here. It is just a conventional table. I'm inserting some rows here. And now you may ask, well, why am I showing this in a JSON talk? Well, I want to show you how easy it is to generate JSON from this relational data. So this is a JSON object operator here, and star means all the columns should be converted to JSON field names. So what you see is that every row gets converted into one JSON object. There are 3 more JSON operators to generate arrays and aggregates, but here, because of time reasons, I'd rather keep this simple. And actually, one more example here, it is case sensitive. So for example, if I type first name in lowercase here, it would actually just use first name. And I could also use, there's some syntax if I don't want the JSON name to be the column name. So that's also possible. Now let's go into the second entity here, which is the courses. And this is a mixture of JSON and relational columns. So you see here, I have a CID, this is for the course ID. The course has a name. It points to a teacher that gives this course. It has some dates when this course starts and ends. And then there's this column flex here, and its data type is JSON. So as I said, I run this on a 21C database where we have this new JSON data type with a binary representation on disk. If I was running this on a 19C, I could also store this as a blob or a clob, and I use the isJSON check constraint to make sure that all the data I insert is syntactically correct JSON. Good, so let's run this create table statement. And the purpose here is to use this as a flex field. So imagine you have a table, but you want to be able to add additional attributes as you go. So instead of adding like 20 flex fields, let's say 10 strings and 10 numbers, we use JSON here now for this flex field. And what I'm inserting here now is some courses. So we have aerospace engineering. The line is cut up here a bit. Not so important. Oh, actually it is, because here the flex field is null. So I'm inserting a null value for the JSON. This is basically when I start out and I don't have any flex field yet, but now in the next insert, we actually insert something about the maximum number of students. So I want to make sure that this course can only be attended by 30 students. And the third course actually has also this max students, but it also has an array of languages here. So I have some information about the languages that this course is available, and I may continue adding new fields as I go. Good. So now I can use this simple syntax here to just extract some fields from the JSON. So I'm selecting from my courses table. This is the name. This is this conventional relational table. Oops, now I scrolled here. But then I have this flex column, and I can extract some values out of this flex column. In this case, it's the maximum number of students, so max students. And I use this number trailing function so that I can extract this value as a number. Similarly, I add this language here, and you see that this array is being returned. I see that this course is available in English and Spanish, and you can also see that if the field is missing, I just get a null value back. I don't get a error back. So this is especially nice for schema flexibility. There's also a way that you can say this field is mandatory. So if it's not there, I want this to be raised as an error. Good. So let's go now to another API here. So I want to show you how to do these collections. So I've shown you like the SQL way of doing things. And there is also an API which we call SODA, and that stands for Simple Oracle Document Access. So this is the same database. It's an always free autonomous JSON database. And I can now just log in. And I'm just going to walk you through this so you can do exactly the same as I do here, because it's an always, you see here, free tier account. And then I go to Oracle database, and I'm using a autonomous JSON database, but I could show the exact same with the autonomous transaction processing database. And here I got a 19C database and a 21. We choose the 21C database. And if I click on tools, on database actions, then I have to log in with a username. So now I have to, so whenever I create a new database, I have to give it like a username, password, etc. So we're logging in. Takes a while here, but this is life. And what I want to show you is that you have these different user interfaces. So there is a SQL interface. This is basically pretty much like the SQL developer that I've shown. This is called SQL Developer Web. So it allows you to run SQL commands. And it also has something called the JSON page. And here you have a collection interface to your data. So now the collection is something that allows you to store JSON data in a named collection, or this is just like a bag of JSON documents. And we want to store our student data in a JSON collection. JSON collection means all my data is JSON. It is not a mixture of relational columns and 1 or 2 JSON columns. Instead, this is all JSON, similar to a MongoDB, for example, where you also have this collection concept. Okay, so I get this message that a collection got created. I see it here, and then I can insert new data. Let me quickly copy this data. I have this in another screen, so you see my head tilting over, and this is one JSON document. So I have a new student, it's John, and he takes these courses C1 and C2. So you see here that I basically have references or link from one document to another table, and we're going to see in a second that we can use joins over this. Okay, let's create another student here, and a third one. So you wouldn't, in a real application, you obviously wouldn't use this user interface to do that. We have language drivers for Java, Node.js, Python, etc., REST, where you can just have simple puts and gets, and you insert your JSON into that collection. So now we see that these are the 3 collections that exist, and we can now run what I've shown before, these query by example. So this is a query by example where I'm looking for all the documents that have a field called courses, and we want to match this against the value C1. So we would probably see this value back as well as this one and not this one here. Let's just quickly run this query. And you see that C1 got matched here as a scalar value, and here C1 got matched because it's a scalar value inside an array. So if you have an array of values, then this QBE expressions actually get matched against all the items in the array, and if one matches, it returns. So this is one example. We could also do, let's say, a class here. We could say class, and the value could be, oh, it's a string 2. And then we only get this value. So it's also possible to do ands and ors, greater, smaller, inequality, etc. This is just a very simple example of a QBE. Good, so now I've inserted this data, and let's go back to our SQL Developer Web. And here our students table, let's see how fast this refreshes here, or our student collection actually is also a table. So if I click here on tables, we see that students has been created, and I could describe it here, and we would actually see it's a table that has 5 columns. It has an ID column, some bookkeeping column when it was created and modified, and most important, this JSON document. This is where our data will reside in. And I can easily convert this JSON data to a text, for example. So I said we store it in a binary format. And with JSON serialize, I can convert it back to a text if needed. Good. So now what I want to show you is that how I can use SQL over this collection data. So what we see here is, for example, that a student takes one or multiple courses, and we can unnest these courses, basically project them out as relational rows using this nested clause. So what I'm doing here, I'm selecting from my students table. I go into the JSON document, I extract the name, the class, and then I say, well, iterate over the courses and give me each course as a separate value. Maybe a bit easier to see the results. So you remember we inserted 3 students, but this query actually gives us more than 3 rows of output. This is because every course is now represented as a separate value in a separate row. So you see all the other columns for the name and the class, they get repeated because they apply for the same student. So this is a easy way to convert your relational data, your JSON data into a relational form. And now you could join this between the other table as well. If you wanted to know what are all the teachers of all students, etc., if you had complex queries, you can easily use this nested path, maybe create views or even materialized views, and use joins if you want to do analytical queries. So now it's a very short talk. Normally I take twice the time, so it's basically just looking very briefly into every different component. So what we did here is we projected out some columns from our JSON data and made it look like a table. And here we were able to take relational data and convert it to JSON. And this is this hybrid use case, this flex field use case. Good. And with this, almost done here. So you can try this out yourself. You can sign up for for an Oracle Autonomous Database, and you get some credits, or you may get some credits, but you actually don't need them because everything I've shown here you can do on the always free tier. And there is actually a workshop that is obviously goes into a lot more detail. That takes about like 90 minutes, and it works with this products, example items, product online shop. And this is the URL. Just scan this with your smartphone, and then you get to the URL, and then you launch the always free workshop, and then you can run this example. Or this explains you how to work with JSON and relational data. It goes into a lot more details. Yes, and with this, thanks a lot, and hope to talking to you soon again. Goodbye.